Hello, Lamai. Let's start the session for today. Right now? Okay. Last day, actually, we were discussing about the simplified form, right? How the simplified forms can be used to solve the problems related to acid-base chemistry, right? That was the last day's session, right? We had done the problems at the page number 22, right? Actually, we had done 6 questions at the class, right? And I have given you 2 questions as homeworks, right? Those are the things we had done last day, right? So today, to begin with, we are coming up with the page number 23, where we are supposed to discuss about the buffer solutions, right? Let's start the session with the buffer solutions today, right? Okay, a buffer solution. What this means, right? Okay, let's discuss about these buffer solutions. Right. Today's discussion is all about buffer solutions, right? Right. So a buffer solution. So buffer solution means a solution which resists to a pH change when you are to add a strong acid or a strong base a little amount, right? When you have to add a strong base or a strong acid a little amount, if your solution won't come up with a considerable pH change, such a solution is considered as a buffer solution, right? Okay, so I'll write it here. A solution which resists to a considerable pH change when a little amount of a strong acid or a strong base is added, right, is known as a buffer solution, right? So this is the definition. This is the definition of these buffer solutions, right? So before discussing about the content and the nature of these buffer solutions, right? Let's discuss the nature of a normal solution, right? Let's discuss the nature of a normal solution. Then only we can have a greater idea or the specific nature or specialty with the buffer solutions. So let's consider what will happen if you are to add a little amount of kind of a dill acid or a strong base to water. Let's discuss about that thing first of all. What will happen if you are to add some little amount of strong acid or a strong base to water? Let's discuss about the pH change there, right? Then you will see the specific nature, the specialty with the buffer solution, right? So let's come up with some water. Let's come up with some water, right? So let's say you are with water. Let's say with 999.9 cubic centimeters of water you are with. And suppose you are adding very little amount of a very little amount of a base to this one, a little amount of a base to this one. Say you are adding some NaOH, you are adding some NaOH with 1 molar concentration. NaOH is kind of a strong base, but just a little amount, just kind of 0.1 centimeter cubes. Let's come up with a solution, the resultant solution, and see what will be the pH there. So at here with water, your pH is 7. Water is neutral. We know the water is neutral, so your pH is 7 at room temperature, right? Let's see the pH of this solution. So at this solution, as you have added some NaOH, now this solution contains NaOH, the Na plus and the OH minus. How many number of moles? The number of moles of NaOH here is 1 into 0.1 into 10 to the power minus 3. The CV value, the number of moles, 1 into 0.1 into 10 to the power minus 3. So 1 into 0.1 into 10 to the power minus 3, that is the number of moles. It is going to be 10 to the power minus 4 moles of NaOH. So 10 to the power minus 4 moles. Right? So let's come up with the pH of the solution. So Na plus is no use, that do nothing to the pH. So if you are regarding the pH of the solution, now the OH minus concentration is going to be what? 10 minus 4 moles in, what is the volume? 99.9. With this, the volume is going to be just 1 decimeter cubes, 1000 milliliters, 1 decimeter cube. So OH minus concentration is 10 to minus 4. So your POH is POH is 4 and your pH is what? The POH is 4. pH is equal to minus log OH minus concentration. So POH is just 4. So the pH is 14 minus 4 means 10. So you see, pH has increased by 3 units. pH has increased by 3 units. If you had add a little amount of strong base, huge change with the pH you observe. If you add some little amount of a strong base to water, let's discuss what will happen if you add a little amount of a strong acid to this water. Let's add the same amount, 1 mole HCl, just 0.1 cubic centimeters, very little amount, right? Just 2 drops from the burette. Just 2 drops from the burette. 1 drop from burette contains 0.05 centimeter cubes volume. Just 2 drops from the burette. So that will give you the same amount of HCl as NaOH. So we'll come up with some solution, some HCl, 10 minus 4 moles. The same amount has added, right, as HCl, as NaOH. So Cl minus do nothing to the pH, and your volume is going to be 1 decimeter cube with this stuff as well. So now you are with 10 minus 4 concentration with H plus. So that means pH is just 4. pH is equal to minus log, right, 10 to base 10 to minus 4, that is 4. So pH is equal to 4 here. So you clearly see the pH has dropped by 3 units if you add a very little amount of a strong acid. So this is what happens. This is what happens if you are to add a little amount of a strong acid or a strong base to neutral water to a normal solution. That is what happens. You could observe, right, some greater change with the pH. pH change can be observed to a great extent by 3 units in this case. Right? This is what happens with the normal solutions. But when it comes to buffer solutions, this kind of thing won't happen. That is specialty with buffer solutions, right? So a solution which resists to a considerable pH change if you add a little bit of strong base or a strong acid is referred to as a buffer solution. So that actually these kind of pH change won't occur with buffer solutions. Those are solutions we are going to discuss today, right? Actually, you can observe a pH change from from the second decimal. So if you are starting with pH 7, by addition of a little bit of a strong base will ultimately leads you to a 7.02, 7.05 kind of a pH. It's a very little increasement, maybe coming up with the second decimal. So if you are to add some little amount of strong acid to a, let's say to a buffer solution with pH 9, so there very little drop will occur. Ultimately, it will give you 8.98 kind of a pH. Very little drop will occur if you add some strong acid or a strong base to a buffer solution. Let's consider them and let's discuss about them today, right? Right. Those are the buffer solutions, right? So let's discuss a bit about the constituents of a buffer solution. So basically, to do this kind of a change, I mean, to resist to a pH change, right? The buffer solution should contain an acid to neutralize the OH minus you are adding, and it should contain some base to neutralize the H plus you are adding, right? So if you are thinking of the constituents of the buffer solution, right? So if you are to observe a negligible pH decreasement when you are to add some HCl, so buffer solution should contain some base here. Buffer solution should contain some base here to neutralize this H plus you are adding, right? It should contain some base here, right? I'll consider it as just B, so that it will react with this added H plus, and you won't observe the appearance of H plus here. So after adding H plus, it will give you BH plus. You won't see the presence of H plus here, as this base will neutralize this H plus added by the strong acid. So to resist to a greater pH drop when adding a strong acid, the buffer solution should have a base in it, to neutralize that H plus added. On the other hand, to neutralize the OH minuses, you are supposed to add from strong bases. The buffer solution should contain some acids as well. Let's consider it as some acid, some HA, acid as well, so that the OH minus added by a strong base will be neutralized by the acid of the buffer solution. So you won't see the presence of OH minus here. But OH minus will be neutralized by this H plus, ultimately providing you some water, right? Not that much of a pH increasement will observe, as the OH minus is not appearing at the flask now, because it has neutralized by the acid of the buffer solution. So basically, to form a buffer solution as constituents, it should contain a base and an acid. Then we have a problem. What is the problem? Can a base and an acid appear like this without reacting? Right? Could a base and an acid appear like this without reacting. Normally we know acids and bases will react. So to appear without reacting, this base and acid should be weak, If these two guys are kind of weak acid and a weak base, then those are not going to react. So buffer solutions contain weak bases and weak acids. To neutralize the H pluses and OH minus added by the strong species. Right? So if you are to come up with a better definition for a buffer solution, one can say a solution containing a weak acid and a weak base which resists to a pH change when adding a strong acid or strong base little amount is referred to as a buffer solution. Right? That is a more clear, more defined definition. So one can say, right, a better definition, a solution containing a weak acid and a weak base right, containing weak acid and a weak base which resist to a considerable pH change when a little amount of strong acid or strong base is added. Is referred to as a buffer solution, right? Buffer solution. Right? See, the idea is clear. So a solution to consider as a buffer solution, it should contain some species which are with some weakly acidic and weakly basic nature. Right? So to consider a solution as a buffer solution, they should contain some species which can show some weakly acidic and weakly basic natures. So as you are with some component with weakly acidic nature, it can neutralize the H pluses added by the strong acids so that the pH won't drop considerably when you add a little amount of strong acid. Right? If your solution contain a weak base, so weak acid, it can neutralize the OH minuses added by a strong base so that as OH minuses are consumed, pH won't increase considerably, right? So that it will show its buffer action, right? pH won't change considerably by addition of strong acid or a strong base little amount, right? So Lamai, we can think of four kinds of buffer solutions like this. We can think of four types of buffer solutions like this. So major idea is you should contain a weakly acidic as well as weakly basic components in your buffer solutions, right? So such kind of four buffer solutions can be seen, right? This is just about the four types of buffer solutions which obey this criteria, right? The four kinds of buffer solutions. Right? Four types of buffer solutions. Number one, right? As this weak acid and this weak base, you can have a weak acid and its conjugate base. A solution containing a weak acid and its conjugate base can be referred to as a buffer solution. A solution containing weak acid and its conjugate base represent a buffer solution. See, if you need an example, a solution containing CH3COOH, the weak acid, and the CH3COO minus Na plus, the conjugate base. So weak acid and its conjugate base. So conjugate base is also a weak base. So that fulfills this criteria, the requirement needed to consider a solution as a buffer solution. This is one kind of buffer solutions available in nature. The second type, you can construct a buffer solution with a weak base and its conjugate acid as well. A solution containing a weak base and its conjugate acids. Also can be considered as a buffer solution. See the situation. So if you are with a solution containing ammonia, which is a weak base, and the ammonium chloride, where you have the NHO plus, the conjugate acid of the NH3, this also can act as an buffer solution. If you add some drops of H pluses, that will be neutralized by the base here, the NH3. If you add some OH minuses, that will be neutralized by the acid here at the solution. That is the second kind of buffer solution available in nature. Already the four kinds are there. The third type, right? You could construct a buffer solution with a weak acid, weak base salt, right? So a solution containing a weak acid, weak base salt, right? This kind of stuff. If your solution, inside the solution, let's say you have this thing, CH3COO minus NH4 plus. This is referred to as a weak acid, weak base salt. So CH3COO minus, which is the conjugate base of the CH3COOH, which is a weak base, NHO plus, which is the conjugate acid of the weak base ammonia, which is also a weak acid. So this section is coming up with some weakly basic character, and this section coming up with some weakly acidic character. So if you add some H pluses to this solution, those will be neutralized by this base present here. And if you add some OH minuses to this solution, that will be neutralized by the acid of the solution. So both the acids and bases can be neutralized by the solution. So pH won't change considerably, right? That is the third kind of buffer solutions available in nature. Let's say the fourth type. So see, with all of these stuff, you could see some species which can show the acidic as well as basic properties. Weak acid and a weak base. weak base and a weak acid. So here weak base and a weak acid, right? The fourth kind, you could construct a buffer solution with the use of a half salt coming from a polyprotic acid, half salt of a polyprotic acid, right? So that is the fourth kind, a solution containing a half salt of a polyprotic acid. What are these things? Half salts of polyprotic acids. If you are to consider this HCO3 H2CO3, the diprotic or dibasic weak acid, it can release an H plus to produce HCO3 minus, and it also can release an H plus to produce CO3 2 minus, right? Showing the acidities. If you consider CO3 2 minus, it can accept an H plus and convert to the HCO3 minus, right? And this guy can accept H plus to convert to H2CO3. So if you are to add some base to this thing, it will convert to HCO3 minus by neutralizing this OH minuses by one of the H pluses. Or one of the H pluses will be neutralized by the OH minuses. If you add further base to this thing, that other H plus is also neutralized by the OH minus to come up with the CO3 2 minus. If you add some H plus to this one, it will convert to HCO3 minus by consuming that H plus. And if you add further H pluses to this thing, it will consume that H plus to convert to the H2CO3. Right? And this is referred to as the polyprotic acid, polyprotic weak acid. So normally it should be a weak acid, right? Polyprotic weak acid, right? This is considered as a polyprotic weak acid, and this is considered as the complete salt of that acid, complete salt of that acid, and this is your half salt. This is your half salt of the polyprotic acid. This is your half salt. See, if you have a solution just containing this half salt, if you have a solution only with this half salt, see, sodium HCO3 minus. There's nothing to do with the Na plus. This HCO3 minus can accept H plus, can consume H plus, can utilize the H pluses and convert to H2CO3. HCO3 minus can react with H plus and consume that H plus and convert to H2CO3. And this HCO3 minus can consume this OH minus or react with OH minus to convert to carbonate. So you clearly see this HCO3 minus alone, just being alone, can utilize both the H plus as well as OH minus. So if you are with a solution containing this kind of a half salt of a polyprotic weak acid, that solution can act as a buffer because it can utilize both the H pluses as well as OH minuses added from the strong acids and bases. Right? Just the appearance of a half salt of a polyprotic weak acid is enough to consider it as a buffer solution. Right? So these are the 4 types of buffer solutions. If you need another example here for these kind of buffer solutions in this type, right? So if you need another example, see, this is another example, right? So I'll erase this stuff to come up with another example for this special kind. Say you have the solution containing the half soles of H3PO4. See, what are those? If you are thinking of H3PO4, which is kind of a polyprotic weak acid, it can neutralize OH minuses by giving off these H pluses there. So first H plus can be given off to utilize the OH minus, so as to convert to H2PO3 minus, PO4 minus, sorry. And another OH minus can be consumed by this one, right, to convert it into HPO4 2 minus. If you have to add some further OH minuses, those OH minuses can be neutralized by the remaining H plus here, and it will ultimately convert to PO4 3 minus. If you are thinking of adding H pluses to PO4 2 minus 3 minus, first it will convert to HPO4 2 minus. Further addition will convert that HPO4 2 minus to H2PO4, and further addition will convert that H2PO4 to H3PO4. So you clearly see these can be referred to as your half soles, this one as well as this one. Even the presence of one of these things will consider your solution as a buffer solution. See, if you are with H2PO4 minus in the solution, it can utilize the OH minuses and convert to HPO4 2 minus. It can utilize H pluses as well when it is converted into H3PO4. So these are also referred to as buffer solution, just containing these half soles. Right? Or you could just come up with a solution containing just this half sole. Right? There's nothing to do with these Na pluses, right? But it is all about the half soles. Right? So these are the four kinds of buffer solutions available in nature. Buffer solutions containing kind of weak acids and their conjugate base, or buffer solutions containing weak bases and their conjugate acids, or buffer solutions containing weak acid weak base soles, and the buffer solutions containing the half soles of polyprotic weak acids. Right? All of these solutions represent buffer solutions. Right? So you can go through your note, right, at the page number 23 and 24, you could see these things are appearing. And remember that in all of these cases, these constituents are considered as weak acids and weak bases. Right? Weak acids and weak bases. Right? Okay? The thing is clear now? Right. Okay, just go to the note Lama. See the page number 23 and 23. 23 and 24. Things are appearing. It's clear. Right. Then, in your question papers, they would ask you to explain the buffer action of a given buffer solution. They would ask you to explain the buffer action of a given buffer solution. Right? Let's try to explain this buffer action of these buffer solutions. Such questions will be frequently asked. Right? Okay, let's try to explain the buffer action of this solution. The solution containing CH2COH and the CH2CO minus Na plus. Right? Let's try to explain the buffer action of the solution. Right? If you had been asked to explain the buffer action of a solution, buffer solution, what you're supposed to do is, right, you have to mention that if you have added some H plus from strong acid, you have to mention that H plus will be consumed, totally reacted by the base in the solution. And then you have to mention if you add some OH minus from a strong base, that OH minus will be consumed, totally reacted by the weak acid in the solution. And finally, you have to mention that as those OH pluses and OH minuses are neutralized by the species inside the solution, you won't observe a considerable pH change. Those 3 points should be mentioned. Right? Let's write those things. So if they have asked you to explain buffer action of this solution, these are the points to count. Right? You can write when a strong acid is added, or one can say when a little amount of strong acid, right? So a little amount is added, those H plus will be consumed by the weak base in the solution. So what is that? That is this CTCO minus. CTCO minus is a weak base in the solution that will consume OH plus added by a strong species and convert it to CTCOH. You have to mention with the reaction as well. So next point, when a strong base, a little amount, is added, those OH minus ions will be consumed or totally reacted by the weak acid in the solution. Right? You have to mention the equation there. So the weak acid here is CTCOH. This is the weak acid here at the solution that will consume the OH minus you adding. So that will convert to what? The OH minus will grab this H plus of your acid. So you will come up with the CTCO minus and H2O. Right? The third point you need to mention is actually as H pluses and OH minuses are neutralized, no considerable pH change would observe. And OH minus ions are neutralized as above. No considerable pH change, pH increasement or decreasement. So adding H plus will decrease the pH decreasement or increasement would observe. So this solution can be referred to as a buffer solution. right? That is how the buffer action will be explained. This is how we are supposed to explain the buffer action of a given buffer solution. See, these things are mentioned at the page number 22, 24. Let's go to that note. Explain the buffer action of a solution containing a weak acid and its conjugate base. Let's go to the note. See, this said me. Explain buffer action of a solution containing acidic acid and its salt. If an acid is added, the H plus ions will be consumed by the conjugate base. They are in the buffer solution, right? And if a base is added, those OH minuses will be consumed by the conjugate acid, the acid component of the solution. Things are clear. So you should be able to comment on the buffer action like this. Clear? Right? These are just some theory stuff, right? About the buffer solutions, right? So after this thing, we'll move towards the calculation part of the buffer things, right? So these are just the theory parts. So normally they will ask you questions about the buffer solutions, right? In the A levels these days, right? Those kind of questions are available in the papers, right? Okay, let's try to explain the buffer action of the ammonium plus ion, that buffer system, right? So let's come up with that test, right? So same kind of explanation is there, even though the equations are a bit different, right? So let's try to explain the buffer action of a solution containing a weak base and its conjugate acid. See this one, solution containing ammonia and ammonium chloride. So there's nothing to do with the Cl minus ions, right? No contribution to pH change. So when a strong acid, a little amount is added, those H plus will be consumed by the weak base in the solution. That is the NH3. So the NH3 will react with the H pluses added by the strong acid. So it will consume the H pluses and that will ultimately form NH4 plus. Anyway, the added H pluses will be consumed. You are not observing a considerable pH drop there as the H pluses are consumed. So when a strong base is added, to this solution, the OH minus ions added there will be consumed by the weak acid there. So weak acid is this one. NH4 plus is the conjugate acid of the NH3, which is coming up with some weakly acidic nature. That will consume the OH minus, react the OH minus completely. So H plus will be provided to here, so that this will convert to NH3 and H2O. So you see, the OH minus are consumed, so that no considerable pH increasement would observe. So as the last point you can write, as H pluses and the OH minuses added from these strong acids and strong bases are totally consumed, you won't observe a considerable pH decreasement or increasement. Right? That is how you are supposed to explain the buffer action of the system containing NH3 and NH4 plus ions. Right now, so you should be able to explain like this. What happens with the help of a double arrow equation as well, right? Okay, so just go to the note there, just go to the note at the page number 24, see whether you are okay with the stuff appearing there, right? right? No. Okay, let's move towards the calculation section, calculation part of these buffer solutions. Right, theory part is clear. No? Very simple things are there in the theory part. Right. Let's move towards the calculations considering the buffer solutions. Right. Okay. So when it comes to buffer solutions, you clearly see this is kind of a type 3 flask. This is kind of a type 3 flask when both the conjugate pair are appearing. When both the conjugate pair are appearing, it's kind of a type 3 flask, right? When considering buffer solutions. In considering buffer solution, type 3 flask is available, right? So as both the conjugate pair are there, right? Let's concern about that thing and let's come up with the calculation part there, right? Okay. So this is regarding the pH of buffer solutions, right? pH of buffer solutions, right? pH of buffer solutions. Right. Okay. So let's concern a system containing the HA weak acid and its conjugate base. Consider a buffer solution containing HA weak acid and its conjugate base. Right? Consider this buffer solution. So now you are with the buffer solution containing HA and A minus. Right? So board is also there in the system, right? So we could think of the equilibrium here. We are the HA will react with water to give you its conjugate base, and as it's an acid, the H2O plus. So here we can come up with the Ka expression. Ka is equal to A minus H2O plus over HA. Right? If you take the minus log both side, I am trying to come up with some relationship, or one can say I am going to come up with some equation which can be used for buffer solutions, right? So taking minus log both sides, we come up with minus log Ka is equal to, I take these two things at once, right? Like minus log A minus over minus over HA. So now this can be considered as this section multiplied by this section. No? This can be written as this section multiplied by this section. So log multiplication is a log summation. So you are taking minus log. So minus log H2 plus. Right? So this can be written as pKa. pKa. This can be written as pH with this minus sign. It is pH. So we can take this thing to here, or we can say we can take this thing to here and this thing to there, right? Okay. So let's take this one. Let's take this one here, right? Take this one here. So it will come up as, right, pKa. This one can come to this side as plus log A minus OHA is equal to pH. Right? I just wrote this thing to here, right? So I subject this pH and write the stuff, right? So we can write pH is equal to pKa plus this thing, right? So this is referred to as the Henderson's equation. Henderson's equation. The pH is equal to pKa plus log A minus OHA. This is referred to as the Henderson's equation. Right? Henderson's-Hasselbalch equation. Henderson's-Hasselbalch equation. So this equation can be used to come up with the pH values of buffer solutions. To do the buffer calculations, this equation is the one we are frequently using. Right? This is referred to as the Henderson's equation. Henderson-Hasselbalch equation, or simply Henderson's equation. Right? If you need to subject pH, what you need to do is this pKa, this bring this thing here, so this becomes plus. Henderson-Hasselbalch equation. Right now? So this can be used, right, to do the buffer calculations. So if you need to write this thing, you can this can be easily write like this. Say you are with some, see this example. Say you are with some buffer solution containing CH3COH and CH3CO minus Na plus. So how to come up with the Henderson's equation? We can write the Henderson's equation as pH is equal to pKa, pH is equal to pKa plus log, at the bottom you have the acid, at the bottom you have the acid, right? At the bottom you have the acid, pH is equal to pKa, pKa, H plus, no, acid, pH, pKa, at the bottom you have the acid, at the top you have the conjugate base. This is the conjugate pair. At the bottom you have the acid and top the base. So at the bottom you have the acid, the CH3COH. At the top you have the conjugate base. See? If you need another example, say you are with some NH3 and NH4Cl, this buffer system. So how to write the Henderson-Hasselbalch equation? pH is equal to pKa plus log, at the bottom you have the acid, you need to come up with the acid. So out of these two, the acid is NH4 plus, the acid is NH4 plus. So NH4 plus at the bottom, at the top is conjugate base, or the base of the conjugate pair. Right now, that is how we are supposed to come up with the how to use that is how we are supposed to use the Henderson equation, right? So for any buffer solution, you can use this thing with the conjugate pair, right? That is clear, right? So this equation will be used, right? And then now, experimentally, they have found that right, this buffer action is possible when only the ratio between the conjugate pair is not exceeding 1 to 10 ratio, right? So they have observed experimentally, after doing much of experiments, the scientists have observed, right, the ratio between the conjugate pair, the HA and the A minus, or CH3COH and the CH3O minus, and the NH3 and the NHO plus, the ratio between the conjugate pair should not exceed 1 to 10 ratio, should not exceed that, to show the buffer action properly. That was the experimental observation with the buffer solutions. That is very clear, Lamai Hari. That is very clear. Why is that? So if you have 1 mole of HA, if your A minus amount is exceeding 10 moles, then you have a problem. So that means your acid there is very limited and the A minus, the base there is very high. So such a solution would be able to effectively neutralize the H pluses but not the OH minuses, as the acid there is very minimal, right? I think you got my idea, that logic, right? Let's say you have a solution of HA and the A minus, and your HA amount is 1 mole there inside solution, and A minus amount is 20 moles. Let's consider that. If such a situation appears, that means your base at the solution is very high and the acid at the solution is very low, 1 mole of acid and 20 moles of base. The ratio is exceeding 1 to 10 ratio. So in such a solution, the solution is capable of neutralizing the acids very effectively, as 20 moles of base is there, but not the bases. Just 1 mole of acid is there. So such a solution can't behave or act as a buffer effectively. To consider as a buffer, the solution should be able to neutralize both the H pluses and the OH minus effectively, not just one species, not just only the OH minuses, or not just only the H pluses. Both the H pluses and the OH minuses should be neutralized effectively for a solution to consider as a buffer, so that it is very clear the ratio between the acid and the base inside the buffer should be, those should come up with some kind of a similar values. Ratio should not exceed 1 to 10 ratio, right? So if you were to apply those things to this equation, we can say, right, if you are applying the ratios here, see what kind of a conclusion we can make with the buffer solutions, right? So if you are applying this ratio, that A minus to HA ratio for considerable buffers, if A minus amount is 1, this X, right, this amount can't exceed 10 units. This is the maximum possible. You can't exceed 10 units. 1 to 10 ratio, that is the maximum possible ratio, right? So if you are applying that thing, your pH is going to be pKa plus log about with this ratio. I am applying 1 to 10 instead of that ratio. This is 10 to the power minus 1. to the power minus 1. That means that is this minus 1 pKa minus 1. And if the ratio is other way around, if you have more A minuses than HA, the maximum possible ratio is 10 to 1. You can't have more than 10 of A minuses than the HA. Then you can't show the buffer action effectively. So if you apply that thing to the Henderson's equation, the ratio is 10 to 1. That means just 10. So pH is pKa plus log 10, that is 1. Log 10 is 1. So the buffer action, can be observed around pKa value of the buffer solution of the weak acid, and it is around pKa plus or minus 1. That is a range, that is referred to as a buffer range. So with the buffer solution, the buffer range could be referred to as the pKa plus or minus 1. Buffer range could be referred to as pKa plus or minus 1. So it's like this now, man. So let's say you have a solution. Let's say you have a buffer solution with a weak acid and a conjugate base, and if say if its pH is pKa is 5, its pKa is 5. Let's say its Ka value is -5 and the pKa is 5 for this HA. So you construct a buffer solution with HA and A minus. So its pKa value is 5. So it can show its buffer action in the range of 5 plus 1 and the 5 minus 1. In the range of 5 plus 1 and the 5 minus 1. That means in the range of pH 4 and 6, this buffer solution can show its buffer action. That is the idea. Right? See, I am coming up with the idea here, this one. Right? The point is this now. So if you need some example, what we are discussing about. Right? Let's say you have a buffer solution made up with HA and the A minus. Let's say Ka value of HA is equal to 10 to the power minus 5. That means its pKa value, which is minus log K, is equal to 5, right? Your pKa is 5. Right? This means in the range of pKa plus or minus 1, in the range of pKa plus 1 and the minus 1, only this buffer solution can show its buffer action. Right? Buffer action of this buffer is possible in the range of pH 4 to 6. That is the idea. In the range of pH 4 to 6. How these 4 and 6 are decided? The 4 is the pKa minus 1 and 6 is the pKa plus 1. So in this pH range, this can act as a buffer. This can act as a buffer. In this range, this can act as a buffer. By varying the amounts of these things, by varying the amount of HA and A minus, you can construct buffers of this range. You can construct a buffer of 4.5 with the use of these two guys. You can construct a buffer of 5.5 with these two guys. You can construct a buffer of 5.85. Any buffer in the range of 4 to 6 pH can be considered with the use of these two guys. Right? That pH is the pH value which is not going to change with the addition of H pluses and the OH minuses of strong acid and strong bases. That constant pH should be in the range of 4 and 6 in this case. That is the idea. Right? So the buffer range is decided by the Ka or the pKa value of the conjugate pair. Right? Okay. So just go to the note there, Lama, and see whether you understood the stuff appearing there. First derivation is done, and then they have discussed about the range. Thus, it is seen that acid-base buffer exists within the range of pH pKa plus or minus 1. Right? So these two chemicals can be used to produce any buffer in the range of 4 to 6. By varying the concentration of these two guys, you can construct a buffer in the range of pH 4 to 6. That is the idea of the buffer range, which will be given by the pKa plus or minus 1. Right? Okay. Let's discuss this idea more properly. Let's come up with some question on this idea. See, let's do the question appearing at the page 25. Right, to get this idea more properly. Right. See, let's go to the question, Lama, and then we can discuss the stuff. So question says that you have a weak acid, you have a diprotic weak acid H2A. The question says you are with a diprotic weak acid. H2A. H2A, diprotic. It can release 2 H pluses, diprotic. Diprotic weak acid. And their Ka values are given. The diprotic means it can release 2 H pluses. The first thing is actually the releasement of first H plus to convert to HA minus. That will be represented by the Ka1. That will be represented by the Ka1. Releasement of first H plus, or acting as an acid for the first time. So converting the HA minus to A2 minus, it is represented by the Ka2, acting as an acid for the second time, releasing the H plus for the second time. Ka2 acting as an acid for the second time. Right? Those values are given. Ka1 and Ka2 values are given. Right? So your Ka1 is given as 1 into 10 power 5. Ka2 is given as 1 into 10 power minus 9. No? Right? Okay. Let's see what kind of questions they are asking and how we are supposed to solve those things. Right? Okay. The first thing, what they're asking is to produce a buffer solution with pH 5.5. To produce a buffer solution with pH 5.5, they're asking which compounds can be used out of H2A, NaHA and Na2A. Right? See, these are the values they have provided. Right? Right? Now what we need to do? We are supposed to come up with a buffer solution, right, with pH 5.5. pH 5.5. So let's consider the pKa values of these two guys and consider the ranges there. The pKa plus or minus 1 ranges, those ranges. See, if you are with the first equilibrium, it's like this, no? H2A reacting with water to give you HA minus, releasing the first H plus, and forming H2O plus, releasing the first H plus. This is referred to as Ka1, right? So Ka1, for this one, the Ka1 is 10 to the power minus 5. So your pKa1 is just 5. So the buffer range, buffer range possible with these two guys, buffer range possible with H2A and the HA minus, that pair is what? 5 plus 1 and minus 1. 5 minus 1 is 4, plus 1 is 6. So with the use of H2A and HA minus, you can prepare buffer solutions in the range of pH 4 to 6. The range of pH 4 to 6. So buffer range is pH 4 to 6. Right? So if you are thinking of the other situation, Ka2, you think of Ka2 situation, Ka2 means HA minus goes to A2 minus. HA minus releasing the second H plus. Releasing the second H plus, acting as an acid for the second time, which is the Ka2. So it will produce the A minus and HCO plus by releasing the second H plus. This is the Ka2. That is 10 to the power minus 9. So pKa2 is just 9. So the buffer range possible with these two guys, with these two pair, with the HA minus and the A2 minus pair, the buffer range possible is pH 9 minus 1, 9 plus 1. It is a range 8 to 10. So with the use of HA minus and A2 minus, you can prepare buffer solutions with the pH values in between 8 and 10. Which is in between 8 and 10. With the use of H2A and HA minus, you can prepare buffer solutions with pH values in between 4 to 6. Right? That is the idea. This is the pair. This is the pair here with the Ka1. So our task is to prepare a buffer solution with pH 5.5. pH 5.5. So we can say pH 5.5 comes inside the range, this one, the range pKa 1 plus or minus 1. pKa 1 plus or minus 1, that is 4 to 6. Right? So to prepare this buffer, these two things should be used. That means H2A and HA minus, means that is NaHA. NaHA should be used. See how we are supposed to consider the species needed to prepare the buffer solution with the wanted pH value. Right? This is the idea. I wish you got the idea of this buffer range. Right? Buffer range means in this range you can prepare any buffer with the use of these two guys. For this equilibrium, you can prepare any buffer in the range of 8 to 10 with the use of these two guys. So our wanted buffer is with pH 5.5 that comes inside the range of this one. So that we have to use these two guys to prepare the pH 5.5 buffer. Right? So this is the answer for the Roman number 1. So just complete this stuff and then we'll discuss the next one, and this is just what is the mole ratio should be added with these two guys to prepare the 5.5 buffer. So first just complete this one. Right now, okay. So let's then discuss the ratio of H2A and HA should be added to prepare this buffer. Right? So let's discuss in which kind of a ratio we need to add the H2A and HA minus to prepare the buffer solution with the pH 5.5. So now we are very sure that pH 5.5 buffer can be made out of adding these two guys. Before that, pH 5.5 comes inside the range of 4 to 6, right? Which is the pK plus or minus 1 of this buffer, right? So let's discuss with what kind of a ratio these two guys should be added to come up with pH 5.5 buffer, right? By varying the ratios of these two guys, you can come up with different pHs between the 4 to 6 here, right? So we need the 5.5 specific pH value now, right? So let's discuss what kind of ratio these two guys should be added to come up with that pH 5.5 buffer, right? Okay. So I'll erase this stuff, right? So this is the Roman number 2. Right? Find out the ratio. H2A and HJ minus should be added to prepare pH 5.5 buffer. Right? For this thing, we can come up with the Henderson's equation. See? So your pH is equal to pKa. Now here this pKa1. We are using this formula. It is pKa1 plus log Henderson's equation. Acid at the bottom. The acid out of these two guys are H2A, and the base at the top, HA minus. It's conjugate base, right? So what we need is the pH 5.5 buffer. What we need is a pH 5.5 buffer. pH 5.5 buffer is needed. So here we will come up with the pH of the buffer solution, right? This Henderson equation can be used to come up with the pH of the buffer solution. pH 5.5 buffer is needed. So we need now pH 5.5 buffer. We are looking for pH 5.5 buffer. Right? I'll write it here. Looking for buffer containing these two guys with pH 5.5. That is the pH value of the buffer solution, right? So pKa, what is the pKa value? pKa value is 5. We are using this relationship, this equilibrium. pKa1 is 5 plus 5 plus, right, log HA minus OH2. So if you bring this thing here and subject this one, we will come up with log HA minus OH2A is equal to 0.5. So this comes to here, right? So this will be subjected there. So you can come up with the anti-log to subject the HA minus OH2A. Anti-log 0.5. So look at the anti-log. 0.5 means 5000. In the anti-log chart, you just have values, 0 point values with 4 decimals. In anti-log chart, you have 0 point values with 4 decimals, right? That is how anti-log table looks like, right? Just go to the log table there. 5000 at the anti-log site. 5000. 5000. Coming up with 3162. 3162. That means 31 is 3.162. So now here the concentration ratio is actually the mole ratio. Concentration ratio is the mole ratio. How come? It's like this, no? So HA minus to H2A concentration ratio means NHA minus divided by the volume divided by NH2A over volume concentration. So the thing is, actually, these volumes will cancel off because both are at the same solution. Both are at the same solution. Same volume is considered for both the species. So same value will be applied for these two volumes. So those will cancel off. Actually, that means this concentration ratio means the mole ratio. In Henderson's equation, the concentration ratio means the mole ratio of the conjugate pair. Concentration ratio means the mole ratio of the conjugate pair. So the concentration ratio is 3.162 to 1. That means mole ratio is also the same. So that mole ratio is also the same. So that we can say the mole ratio is same 3.162 to 1. Right? The concentration ratio is same as the mole ratio. Right now? So that is the answer. Clear? So do the working and then we'll discuss the second question. See how the Henderson's equation is used to solve the problems related to buffer solutions. You had a buffer with pH 5.5, so that is the value, the pH 5.5, that is the pH of the buffer solution given by the Henderson equation. So pKa value is 5. We are using this equation, that means pKa1 is used, it's 5. So that's the concentration ratio. The concentration ratio is same as the mole ratio. Mole ratio, that is what they ask. Right now? So complete this stuff and then we can do the second question as well. But this is actually A, no? This is actually A. It's actually A, right? Question number 1, no one can say A. Complete this stuff. Right, now let's discuss the second question. Right? The part B of these buffer questions. Right? Is clear? No? Right. Right? Let's move towards the next question. Right? Third part B, no? What they asking in the part B? See, it's like this. To produce a buffer solution with pH 8.5, to produce a buffer solution with pH 8.5, what they're asking is, right, find out the mass of HJO Na2A, which should be mixed with 100 centimeter cubes of 0.1 mole NaHA solution. Right. So what they're asking is, you're supposed to produce kind of solution with pH, solution with pH 8.5. So you are coming up with buffer solution with pH 8.5 needed to be prepared by mixing what? HAONA2A with 0.1 mole 100 cubic centimeters NaHA. So in the solution NaHA is there, 0.1 mole 100 cubic centimeters, right? What they are asking is, what they are asking you is to find out the mass of HAO or the Na2A. So they are saying HAONA2A mass need to be added. This is the question. Right? So you are supposed to prepare pH 8.5 buffer by mixing one of HAONA2A, it should be H2A, right? One of H2AONA2A to HA minus. So here the HA minus is needed, right? So no use with the Na plus here, right? Okay. Right. So definitely at this buffer solution, one component is the HA minus. One component is the HA minus. We need to come up with the other component first of all. We need to come up with the other component first of all. Before coming up with the mass and the ratios and the stuff, first we need to find out the other component there should be to prepare this buffer. What is the other component there should be? Right? To prepare 8.5 buffer. So 8.5 value comes inside the range of 8 to 10. Inside the range of 8 to 10, which appears with the pKa 2 plus or minus 1. If you consider pKa 2 plus or minus 1, the range is buffer range coming up as 8 to 10. This 8.5 appears inside that. So for this, we need to consider the Ka2 equilibrium, because inside the pKa 2 plus or minus 1, that 8.5 pH appears. Inside the pKa 2 plus or minus 1, which is the 8 to 10, this 8.5 appears. So we need to consider the Ka2 equilibrium to construct this buffer. This is the first thing, right? So we can say pH 8.5 comes inside pKa 2 plus or minus 1. That means pH range 8 to 10. So to prepare the buffer, right, that equilibrium, Ka2 equilibrium, coming up with these two guys, Ka2 equilibrium coming up with these two guys, to prepare the buffer, or one can say as component of the buffer. So as component of the buffer, HA minus and A2 minus should appear. Right now? Okay, the thing is clear now? So the other species here should be here is the A2 minus is the A2 minus is the A2 minus. Right now? That's the first consideration. We need to prepare pH 8.5 buffer, right? So that value is appearing actually in between the pKa2 plus or minus 1, 8 to 10 range. So that the conjugate pair coming up with the pKa2 is the HA minus and the A2 minus. So those are the two components should be there inside the buffer solution. So we need to consider the A2 minus. So that is this one. So the Na2A should be the species to add. Na2A should be the species to add to HA minus to prepare this 8.5 buffer, first of all. Now our task is to find out the mass of the Na2A should be added. Find out the mass of the Na2A should be added. Right? So let's count with that. Finding out the mass of Na2A should be added. Right? Mass of Na2A should be added. Right? Okay. So let's come up with Henderson's equation. Right? For this equilibrium, what is the equilibrium? The equilibrium between these two guys. So that can be considered as HA minus hydrolysis right? Ka2 equilibrium, Ka2 equilibrium, right? So Henderson equation, pH is equal to pKa2 plus log the acid at the bottom, HA minus conjugate base at the top. Right? So pH of the buffer needed is 8.5. pKa2 value is 9. Ka2 is 10 to the power minus 9. pKa2 is 9. pKa2 is 9. Right? pKa2 is 9. Clear? Right? So your Ka2 is 10 to the power minus 9. pKa2 is minus log Ka2 minus log 10 to the power minus 9 is just 9, right? Is 9 plus log A2 minus OHA minus. Right now. So let's try to do the last calculation there with the page number 25. Right. So what they are saying is, now you had prepared this buffer solution. No? So now they have added some HCl to this buffer solution, and they are asking the final pH of the solution. Final pH of the solution. So if you are adding a strong acid or a strong base, a little amount to a buffer solution, what we are expecting is, right, no considerable change in pH, no considerable increasement or no considerable decreasement in pH, no considerable increase or decreasement in pH. That is what we are expecting when you are adding an strong acid or a strong base to this buffer solution, right? So no considerable pH change means that not that much of change, not that much of a change. It not means that no change at all. It is not means that no change at all happens, right? Some very little amount of pH will drop or increase, right? So in this question, we are supposed to find the pH value, right? So normally with the second decimal, kind of a change will occur, right? Very negligible change. So let's do a calculation to come up with that change or come up with that final accurate exact value, right? So see how that calculation is done. Right. So in this case, Lamai, what are the amounts of these guys added? So ultimately now you have a solution. So I'll do that thing. So with the question C, start with the buffer solution we just prepared, right? So that solution contains, right, HA minus and A2 minus. What are the amounts there? The A2 minus amount is this much, 3.16 into 10 to the power minus 2 moles. That HA minus amount was just like it was kind of 0.1 mole 100, no? That is 0.1 mole 100. So 10 to the minus 2, no? This is 1 into 10 to the power minus 2. Such 100 milliliters were there. This was the buffer solution we just made. Right? So this is the buffer solution we are with pH 8.5. Right? What we are supposed to find out now is, actually the pH of the solution after adding some strong acid HCl, what is the amount? 1 into 10 to the power 4 minus 4 moles, very little amount of HCl. This is the same amount of HCl we had added to neutral water at the start of the lesson. At the start of the lesson, we had just, right, added 10 to the minus 4 moles of HCl as well as 10 to the minus 4 moles of NaOH to water, and seen the pH change would occur there. Some 3 units of pH change has occurred when you are adding HCl this amount as well as NaOH this amount to neutral water. Now we are going to calculate and show what kind of a pH change would occur with this buffer solution if you add the same amount of HCl, the strong acid, right? So we are supposed to come up with the pH of the final solution here, pH of this solution. We are expecting some negligible change of pH, right? We are expecting some value around 8.5. We are expecting some value around 8.5, right? See whether we are able to come up with such a value and prove the buffer action of the solution, right? Okay. So how to do this stuff, right? So first of all, let's come up with the equations possible here. Let's come up with the equations possible here. So HCl is added to this solution. So HCl is kind of acid, so that the base in the solution will react with this acid. So as this one is a kind of acid, the base in the solution, which is this one, will react with this acid, right? The H plus will be grabbed by the more basic guy here. The A2 minus is more keen of H pluses, as the negative charge is there, greater there than the H minus, HA minus. So A2 minus is a greater base than the HA minus, right? Because the negative charge is greater there, so we'll attract H pluses easily. So this acid will react with base. So normally when you are doing these kind of additions, the strong acids and weak base, strong bases like that, we firstly consider the straight arrow reaction. After that only we are considering the double arrow reaction. The things are clear, no? First consider straight arrow reaction, then consider the flask at the end of the straight arrow reaction, then applying the double arrow reaction. That is what we are. That is how we are solving these kind of problems, no? Right, okay. See, the first thing. So HCl will react with the A2 minus here. So HCl reacts with A2 minus, which is the base, which is straight arrow reaction, because this one is kind of a strong acid. So straight arrow reaction to come up with the HA minus and the Cl minus. So the amounts should be written in terms of moles, as it's a straight arrow reaction. So the numbers are like HCl added amount is 1 into 10 to the power minus 4 moles. At the start you have 3.16 into 10 to the power minus 3 moles. At the start you have here as HA 1 into 10 to the power minus 2 moles. Right? So you clearly see this one is a limit reagent. Right? So that will be added to the salt. That thing will totally consumes and added to the salt, convert to the salt. So we can consider this one as in terms of 10 to the power minus 3. Right? Let's take this one in terms of 10 to the power minus 3. That is like 0.1 into 10 to the minus 3. It is 10 to the minus 2. It is 0.01 into 10 to the minus 2. Right? So that will be added to this one. So this will be totally converts as it is the limit reagent and added to this one 0.01 into 10 to the minus 2. Right? Will be added, and from this excess reagent it will be deducted. Right? It will be deducted. That is 0. So if you are taking this one as 10 to the minus 2 value, it can be written as 0.316 into 10 to the minus 2. I'll take it all the values as 10 to the minus 2 values, so for the easiness of the calculation, right? So that will be deducted, minus 0.01 into 10 to the minus 2. So ultimate values are at the end of the straight arrow reaction, you come up with some A2 minus, which is the amount. It is going to be, right, 0.306 into 10 to the minus 2. That is the amount of A2 minus at the end of the straight arrow reaction, and the HA minus at the end of the straight arrow reaction is just added, right, 1.01 into 10 to the minus 2 number of moles. So after the straight arrow reaction, we are considering the flask. Now you have this kind of flask containing what? The A2 minus and the HA minus, right? So for this flask, we can copy the Henderson's equation. to find out the pH, right? So considering this flask, we can come up with the Henderson's equation. Before that, let's come up with the Hydrolysis reaction, right? So you have the HA minus hydrolysis to concern. It will produce the A2 minus as well as H2 plus. So if you are considering the Henderson's equation there, so pH is equal to pKa2 here. This is the Ka2 expression, right? Plus log. At the bottom you have the acid Ha minus. At the top you have the conjugate base, right? So apply the values. pKa2 is this value. pKa2 is this value, right? Ka2 is 10 to minus 9, that means pKa2 is 9 plus log. Actual now this concentration ratio is same as the mole ratio. Concentration ratio is same as the mole ratio, right? So mole ratio is this, right? So A2 minus amount is 0.306 into minus 2. HA minus amount is 1.01 into minus 2, right? So you can copy the pH. Here pH is equal to 9 plus log. What is this value? 0.306 divided by 1.01. 0.306 divided by 1.01. That is 0.3029, right? So let's count it like this. Lack of space there, right? 9 plus log 0.3029. So this is just this value. So we can write it some as 3.029 into 10 to the power minus 1, right? 10 to the power minus 1 comes to here as you can take the 10 to the minus 1 out. So it is going to be 8 plus log 3.209, right? No? So this thing can be written as like this, no? So 10 to the minus 1 can be taken out. So minus 10 to the power minus 1 can be taken out as minus 1. So minus 1 plus 9 is 8, and this value log 3.029, log 3.029. So 3029. That is like 4.8. 9 is 13, no? 4.813. 3029. 4.813. 0.4813. So the value is 8.4813. That is the pH value at the end of this process. So at the end of the situation, your pH is what? Your pH is pH 8.4813. See, very negligible pH change. You have started with 8.5. At the end, you have 8.48. Let's see that like this. 8.48. See, very negligible pH change occurred with the addition of a strong acid. The same amount, right? Earlier we had added to the water at the beginning of the lesson, right? At the start of the lesson, the same amount is added to the water. We had seen some treats of decreasement of pH when it is added to the water, the same amount. But with this to this solution, for this buffer solution, just 0.02 units of change there. just a negligible change in pH, just coming from the second decimal point. Clear, no? So just do the working. This is how this kind of a calculation will be done, right? Okay. Right, Niloy? So with this one, we are winding up the session for today, right? Just copy the board, right, and go to the calculation, right? So you can do the same kind of calculation with the addition of NaOH as well. Just do at home. Just try to add some same amount of NaOH to this buffer solution and see what kind of a change would occur there. Just the change in the second decimal place you would observe. Just go to that thing and see what kind of change would be possible. Right, do that at home. Just add some 1 into 10 power 4 moles of NaOH and see that change, right? So with this one, just wind up the session for today, right? So I'll leave the board to copy it down, right? And then goodbye then. See you next week. Good night.